In the previous section, we talked about triple integrals in rectangular coordinates. We now want to change over and talk about doing triple integrals in different coordinate systems. In this case, the cylindrical and spherical coordinate systems. These, you may remember, are the coordinate systems that we reviewed late in chapter 2, I want to say. And the idea here is you may remember when we did double integrals in the context of rectangular coordinates, then we did double integrals in polar coordinates. And you remember that there was this extra factor of r that we had to include in all double integrals involving polar coordinates. We're going to see that happening again here with cylindrical coordinates and spherical coordinates. We're going to have to introduce these somewhat mysterious factors in order to do integration in these alternate coordinate systems. These are not the only two coordinate systems or three coordinate systems that that we encounter in applications, but they're certainly the most common. Rectangular, cylindrical, spherical are the most common coordinate systems. That's why we focus on them here today, or here in this textbook. The goals for this particular section are relatively straightforward. We need to be able to evaluate triple integrals in cylindrical coordinates and evaluate triple integrals in spherical coordinates. There's a lot buried in those two statements. I want you to be able to describe volumes using cylindrical coordinates or spherical coordinates. I also want you to be able to decide which coordinate systems are best for a particular geometric situation. All of this, again, this is a very skills-based section in a very skills-based chapter. All of this is going to require you to do a lot of problems and just kind of go with the flow and develop an intuition for these kinds of exercises. Let me go back to my notes here. So the big idea here, why are we even bothering to do integrals in different coordinate systems? It's because sometimes the shape of a problem motivates one particular coordinate system over another. And you might say, what do you mean? Like, why would the coordinate system matter? And it turns out that if you choose the right coordinate system, usually it's going to make the calculations easier. So if you have some kind of physical system where there's lots of cylindrical symmetry, you might want to try cylindrical coordinates because the expressions and mathematical symbols that you write down in that situation are going to be sort of really well described by cylindrical coordinates. Similarly, if you have a problem with lots of spherical symmetry, then spherical coordinates are going to be the right choice. And it is definitely the case that there are problems that are impossible in rectangular coordinates that are trivial in cylindrical coordinates or simple in spherical coordinates. The more you work with these, the more you'll get an intuition about which coordinate systems to choose. That said, if you start going down one road, you decide I'm going to use cylindrical and it doesn't really pan out, back up and try going down spherical, or maybe stick with rectangular and see what happens. So, it's an art as much as it's a science in choosing the correct coordinate system. There are dozens of commonly used coordinate systems, but we're only going to focus on these three coordinate systems here today. Let's do a quick flyover of the section before getting into some of the exercises. This section does reviews of both cylindrical and spherical coordinates. This is convenient. It makes it so that you don't have to go back to chapter 2 to review that material. And I think it's probably a good idea for everybody to really look over these two ideas again, the cylindrical and spherical coordinate systems. The big takeaway here, or one of the two big things. Number one, we need to be able to describe regions of integration in these different coordinate systems. And number two, we need to understand this extra factor. In cylindrical coordinates, for example, in rectangular coordinates, we were summing up little boxes, little cubes, and each of those little cubes was essentially the same size, no matter where you were. In cylindrical coordinates, we're still summing up little cube-like objects. We're still dicing up our region of integration. But if you look closely, because of the nature of the polar coordinate system that's sitting down here in the XY plane, and that of course makes a big part of the cylindrical coordinate system, we see that the little cubes that we're summing up, the size of those cubes, the volume of those cubes depends on where you are, and in particular how far you are from the z-axis. This little cube here is much, much smaller than this cube out here. What determines the difference? The distance from the z-axis, the r variable. Conveniently for us, we can fix this little problem by simply introducing an extra factor of r in the Riemann sum. And when we take the limit, that r appears as a factor in the integrand. So if you're doing double integrals in polar coordinates, you get an extra factor of r. Same thing here. If you're doing triple integrals in cylindrical coordinates, you get that extra factor of r. So the volume element dv in cylindrical coordinates is r dr d theta dz. Now the order in which we integrate, you can shuffle that around as much as you like, but the r has to be there. That extra factor of r has to be in the picture. So Fubini's theorem is fine with swapping the order of integration, but this little r has to be present if you're integrating in cylindrical coordinates. We'll talk a little bit more about how to describe volumes in terms of cylindrical and spherical coordinates in a moment. I want to go ahead and just talk about this issue in the context of spherical coordinates. So you'll remember that spherical coordinates describe points in three-dimensional space using the parameters rho, phi, and theta. Rho is the distance that the point is from the origin. Phi is the angle from the z-axis. And remember, it starts at 0 when we're along the positive z-axis, and it goes all the way around to pi when we're pointing along the negative z-axis. And that's the only range of phi values that you really need to consider, from 0, North Pole, around to pi, South Pole. And the last variable in the spherical coordinate system is theta, and that's the angle that the point makes with the x-axis in the xy plane. So it kind of rotates you around. Remember, when we studied this, we thought about latitude and longitude on Earth. That's a good metaphor here. Okay. Now, when you're building integrals in either cylindrical or spherical coordinates, I want you to kind of imitate the process that we've been doing in rectangular coordinates. And that is, we decide an order of integration, and then we pick paths that are parallel to each of the variables that we're integrating with respect to. So remember that if we decided we were going to do dz, dy, dx, we would first start by looking at little paths parallel to the z-axis. Once we figured that out, we would squash it down onto the remaining two variables, x and y. Then we would look at paths parallel to the y-axis. Once we figured that out, we would squash it onto the last variable, the x variable, and then there's only one path there, and it's the interval on the x-axis. Similarly here, not exactly analogous, but similarly, you have to decide in cylindrical coordinates what your order of integration is going to be. dr, d theta, dz, d theta, dr, dz, etc. Let's think about just dr, d theta, dz. So in that case, you look at the volume that you're integrating with respect to, and if you're doing dr first, then you want little paths that are parallel to the r direction. What is the r direction? These are rays that emanate from the z-axis. So you figure that out, and then once you've figured out r, you kind of collapse it into what's left, which is the z theta direction, and that's where this kind of breaks down. When you collapse in the theta direction, what you're doing is collapsing onto circles around the z-axis, and then you figure out what's a path that's parallel to theta. It's these circular arcs, and you figure out where does it start, where does it end, and those are the limits in the theta direction. Once you finish that, then you collapse it onto the last variable, in this case z, and the whole thing collapses down onto this line segment on the z-axis, and then we just pick off the lower c, the upper d. A very similar process happens in spherical coordinates. You decide the order of integration, and then you think about, let's say you're going to do d rho, d phi, d theta. So here we would first look at paths in the rho direction. So those are paths that are parallel to rays from the origin. And then maybe you're looking at the phi direction. So those are arcs in the phi direction. And then finally the theta direction, those are arcs going around the z-axis. I promise if you start gently and build your way up, you will develop an intuition for this. The last thing I want to mention before we get into some of the exercises is, just like in cylindrical coordinates, these little volumes depend on where you are in space. If you look at this little volume and you move it towards the origin, you can see that it gets smaller, it gets pinched down. So the volume of that thing is going to get smaller as it goes to the origin. But here's something that doesn't happen in cylindrical coordinates. In spherical coordinates, as you sort of move around in the phi variable, if you get close to the North Pole, you can see that it kind of pinches down, and this volume shrinks as I go to the North Pole. And it grows and gets really fat as I get out to the equator. And then you don't see it here, but you can imagine that as I go take this little piece of volume and I rotate it in phi towards the South Pole, the same pinching is going to happen at the South Pole, and it's going to shrink down to 0 again. Now, there's a lot going on with this formula, but the right factor to introduce in order to account for the variability in the volume of this element, the correct factor to introduce is rho squared sine phi. Rho squared gets really small as rho gets small, right? As rho goes to 0, rho squared goes to 0, and that's telling you that this volume shrinks to 0 as I get close to the origin. A little more subtly, phi. When phi is near 0, this little volume chunk is up here where it's getting pinched together at the North Pole. That corresponds to phi equals 0. Sine of 0 is 0, so sine of something close to 0 is very small. So this factor of sine is scaling this volume to be small, to be close to 0 when it's at the North Pole. It also works at the South Pole. Remember, at the South Pole, phi is near pi. Do you remember what the sine of pi is? It's 0. So as we get close to the South Pole, phi gets close to pi, and this factor of sine of phi gets close to 0, and so it's scaling this volume again properly as it goes towards the South Pole, as it gets pinched and made small. So that's a heuristic argument for why this factor is the way it is. We'll actually see in section 5.7 exactly where this formula comes from, and I'll save that reveal for a couple of lessons from now. I want to move to the end now and just talk about a few exercises. Most of the work in this chapter is best learned by doing, and so I'm going to go through a selection of exercises here, starting with problem 246, and hopefully you'll get the hang of it. not sure why I don't have 246 pasted right in here, but let me just go grab it. So 246, we are asked to compute the triple integral over the solid E. So let me go up here and introduce that for us. And then let me grab the exercise. Almost there. Okay, let me check my notes here. All right, so in the following exercise, we're asked to evaluate the triple integral over the solid E. Looks like a little bit of a typo there because the solid here is actually B. I should make a note of that, and I will do that. And typo, I'm just writing that in my notes here so I can report it up to the textbook authors. All right. So we want to evaluate the triple integral over the solid E. Let's look at this shape. I'm going to try to figure out what this volume looks like by first focusing on this condition. So here we have x squared plus y squared is greater than 1 and less than 9. If it's not clear to you what that should look like, why not switch to looking at the lower limit and the upper limit separately. So in the lower limit we have 1 equals x squared plus y squared. That's just a circle of radius 1. In the upper limit we have x squared plus y squared equals 9. That's a circle of radius 3. Like that. Now we're also asked to assure that y is less than or equal to 0. So where is y less than or equal to 0? Below the x-axis, so I'll do a little bit of shading here. And then finally, we're just going to imagine this, but z goes from 0 to 1. So it's very straightforward. Z starts at the xy plane and goes up to 1, and it's flat. So can you imagine what this looks like? Here's the base of this figure, and it just is drawn up to fill out a volume 1 unit high. All right, let's, what do you think are the best coordinates to use in this situation? You do see a lot of circles, but you don't see any spheres here. Mostly you see cylinders because this thing is really a circle that's extended up 1 unit, and then the outer circle also extended up 1 unit, and those are cylinders. So let's see if we can't use cylindrical coordinates to describe this integral. Let's choose an order of integration. It's not super important which order you choose in this particular case, but because everything is sort of constant limits, I'm going to just do dr, d theta, dz, like that. And since we're doing cylindrical coordinates, we always need this extra factor of r. And then finally, we have the integrand. Or not finally, we also have the integrand x, y, and z, like this. Now, the inner integral is with respect to r, and remember I said as you build these integrals, you want to move in directions parallel to r, and those are radial directions, right? That's parallel to r. And any radial segment like this that's inside the set is going to start at r equals 1 and it's going to end at r equals 3 because this is 1 and this is 3. So we've taken care of that. Now theta. Remember that theta is asking you to look at segments that are parallel to the theta direction. Those are arcs in the xy plane. Where does theta start and where does it end? It starts out here at pi and it goes around to 2 pi. Pi to 2 pi. And you want to be careful here. You don't want to say that it starts at 0 and it goes to minus pi. You don't want to say 0 to minus pi. What's wrong with that? That's not increasing theta, that's decreasing theta. and you're always writing these integrals in the direction of increasing variable. So I could have written minus pi to 0. That would be legit because you would be starting here at minus pi and ending up here at 0. Or if you just want to stick with positive numbers, you can go from pi to 2 pi. All right, the periodic nature of theta gives us some choices over which intervals to use. So I'm going to go from pi to 2 pi. And what's left now is just to smash this onto the z-axis. And if you smash this onto the z-axis, it's going to cover the interval from 0 to 1. Okay, there's one last thing that we need to do, and that is replace x with r cosine theta, replace y with r sine theta, and replace z with z. Z stays the same in the Cartesian cylindrical coordinate system. All right, let's continue this by actually inserting what f actually is. In this case, f is the square root of r squared cosine squared theta plus r squared sine squared theta. And that resolves into just the absolute value of r, right? Because the cosine squared plus sine squared turns into 1. And since our radius here is always positive on this particular set, we don't need the absolute value, so we can just use r. That often happens when you're using cylindrical coordinates. So to finish this, 0 to 1 in z, pi to 2 pi in theta, and 1 to 3 in r, and f of x, y, and z is secretly r. Don't forget the other r from cylindrical coordinates, and then dr, d theta, dz. Now, as is often the case when you're working in either cylindrical or spherical coordinates, you see the integrand here does not have any theta dependence, nor does it have any z dependence. You can grind out this integral, that's great, but you can also rewrite this as just 0 to 1 dz, pi to 2 pi d theta, and then 1 to 3 r squared dr. And the only one of these three integrals that actually requires a serious amount of work is the third one. For example, the first one, if I integrate z dz, I get 1 minus 0, which is just 1. If I integrate theta, I get 2 pi minus pi, which is just pi. The last one, on the other hand, is r cubed over 3 from 1 to 3. That one we actually have to plug in 3, plug in 1, and subtract. Doing so, we get pi times 3 squared minus 1/3. Okay? How did I get 3 squared? Well, I had 3 cubed over 3, that's 3 squared, and then plug in 1, that's just 1 over 3, 1/3. That's the final answer. Cylindrical coordinates is the right choice here. You could try to do this in Cartesian coordinates. You could also try to do it in spherical coordinates. I think it's might be interesting for you to try just to see what some of the snags are that you encounter. All right, in problem 250, you're asked to express the region in cylindrical coordinates, which by my reading just means come up with limits of integration for the triple integral, and then convert the integral to cylindrical coordinates, which for me is just, fleshing out what f and dv look like. And I guess the limits of integration. So just to get a grip on this, I recommend, especially at this early stage, that you sketch, although honestly, at even me, I've been doing this a long time, I still sketch. I'm going to sketch first what's happening in the xy plane, or as the book calls it here, the r theta plane. And in the r theta plane, that's not r. This is x, this is y. In the xy plane, in r and theta coordinates, r equals cosine theta. You may or may not remember this. This was a circle that was offset from the origin, a circle of radius 1, like this. sorry, a circle of radius, what, 1/2, I guess, offset from the origin. So we'll call this 1 right here. And how do we see this if you don't remember? For example, when theta is equal to 0, right, we're sitting here at this point, theta equals 0. You plug theta equals 0 in here, you get r equals 1. So in polar coordinates, that's the point that's 1 unit from the origin and makes an angle of 0 with the x-axis. So that's where we are. And you can kind of follow this around. You can increase theta up to pi over 2, right? And you're going to travel this way along the circle until you get here. That's theta equals pi over 2. And alternatively, you could decrease theta and go around the bottom part of the circle until you get here, and that would be theta equals minus pi over 2. So a nice interval that fully describes this circle in the xy plane is just minus pi over 2 theta to pi over 2, like that. And indeed, those are going to be the limits of integration in the theta direction when we finally do get to that point. All right, so this is the E is bounded by this right circular cylinder. Well, where is the cylinder? The cylinder is this figure in the xy plane and then lifted up parallel to the z-axis until it hits the sphere of radius 3 up here. How do I know this is a sphere? Well, you may remember that r squared is secretly x squared plus y squared. And then z squared equals 9. That's just the equation of the sphere in Cartesian coordinates of radius 3. So now I'm going to do something that we haven't really done before, or certainly haven't done often. I'm going to do a side view so that I can get a better idea of what this volume actually looks like. So this I'll call side view. The cylinder, the base of the cylinder is sitting here, right, from 0 to 1. I've changed my scale here. So over here, each grid square is worth half a unit. Here, each grid square is worth 1 unit. And now I'm going to paint the side view of the sphere in here, right? This is the sphere of radius 3, and we're looking at the side view of it. So it goes something like this, right? In what I'll call the RZ plane. So this R axis is kind of a pretend axis, but what it really is just the side view of the XY plane. And moving along the R axis is really just moving a distance from the origin in the XY plane. So remember that we've got this cylinder that we've generated by taking this circle and lifting it up to the surface of the sphere. Let me change this to red. Lifting it up to the surface of the sphere, and we get something like that. It's kind of hard to really do it perfect justice, but we're talking about the inside of a cylinder that looks like that, where the bottom is flat, cut off by the XY plane, and the top is kind of curved. It's got a bit of a dome shape to it, and it's cut off by this sphere of radius 3. So hopefully you can sort of put these two pictures together and get a full idea of what this volume looks like. It remains for us to now construct this integral. So the triple integral over E of f of x, y, and z dv is going to be a triple integral. We've got to choose an order of integration. I'm going to choose z first because I feel like going from the xy plane up to the surface parallel to the z-axis is sort of an easy first integration. So we're going to go dz, and then we'll do r, and then we'll do theta. Why not d theta dr? The reason for that is r actually depends on theta. So we have to do our r integration before we do our theta integration. Otherwise, the variables that describe the r coordinate will be kind of unresolved by this integration. Okay, now we're doing cylindrical coordinates, so there's an extra factor of r that always appears in the integrand of a cylindrical integral. Z is going to start at 0 on the xy plane, and it's going to go up to this surface. So we're going to solve for z in terms of r. That gives me z plus or minus square root of 9 minus r squared. And of course we'll take the positive one because we want the upper half of this sphere. So the upper limit is just 9 minus r squared, like that. Okay, moving to the next variable, r. We're going to go and focus just in the xy plane now. We've accounted for the z direction, so we're going to squash the red volume down onto the remaining two variables, r and theta. R is always going to start at the origin and go out to the curve. So the lower limit is always going to be 0, and the upper limit is going to be this cosine of theta. That's the curve. Finally, we've accounted for the r variable, the z variable. We've got theta. Over what range of theta values are we going to trace out this circle? We've already discussed that. That's minus pi over 2 up to pi over 2. Now we've got the integrand that we haven't accounted for yet. Now we're not given an explicit integrand in the problem. We're just given f of x, y, and z. So what do they mean by converting this integral? What they mean really is just dropping in the cylindrical coordinate transformations. So I'm just going to move this integrand out a little bit, and we'll say f of r cosine theta, r sine theta, and z. And that's how we convert f from rectangular coordinates x, y, and z to cylindrical coordinates r, theta, and z. And that's the integral. That's it. We're done. We can't do this integral because we don't know f explicitly, so we just leave it like this. All right, in exercise 262, find the volume of the solid whose boundaries are given by the rectangular coordinate equations. Once again, I like to just try to sketch the various pieces and see if I can't figure out what's happening. So what we see here is a sphere of radius 1 and a cone. I'm going to do a side-on view, sort of like I did in the previous example, where I can't actually see the xy plane. And I'm going to sketch these elements in. So I'm going to use, maybe call this 1 and this 1, minus 1, minus 1, like that. And I'll just sketch a circle in. So this circle is actually the side view of a sphere of radius 1. And I'm going to stick the side view of this circular cone in here as well. That looks like this and like this. And if we were to take a cross section of this cone, it would be a circular shape. Now we're interested in the volume that's inside the sphere and inside this cone. All right, and it's just the upper part of the cone. It's not plus or minus square root, so it's just the upper part. All right. Now, I'm going to use, I think that this is a good spherical problem. So I'm going to try to do this in spherical coordinates. Why do I like this as a spherical problem? Let's write the order of integration. I'm going to do d rho, d phi, d theta. And since this is a spherical integral, we always have the factor rho squared sine phi. And I'm going to choose the order of integration d rho, d phi, d theta because in the rho direction, I can start at the origin and go and raise out to the sphere. And that's a really nice situation for spherical coordinates. Those rays always start at rho equals 0 and they always end at rho equals 1, right? On the surface of the sphere of radius 1, every point is 1 unit from the origin. So as rho travels from the origin out to the sphere, it travels a distance from 0 to 1. I'm going to move this out a little bit so that I have more room. That leaves phi. All right, so let's get rid of these rho tracings and focus on the phi tracings. Whoops. Maybe I won't get rid of the rho tracings. I'll just trace them here. Right? In phi, we're doing these kinds of arcs from the North Pole out to the cone. Where does phi start and where does phi end in that situation? Phi is always starting on the North Pole, so it's always starting at phi equals 0, and it's going out until it hits the boundary of this cone. And because this cone is this nice sort of line of slope 1, we know that the angle in there is pi over 4. So the maximum angle is pi over 4. Now you might say, hey, wait a minute, Schuler, doesn't it go from minus pi over 4 out to pi over 4? And the answer is no. Remember that phi just goes from the north to the south pole, right? It doesn't go around the North Pole, it goes from the North Pole to the South Pole. At the North Pole, it's 0. At the South Pole, it's pi. To get out to this cone only requires us to go from 0 to pi over 4. And you're like, but wait a minute, what about the other half of this volume? We're going to miss something. And let me reassure you that we're not going to miss anything because phi only has to do half the job. Theta is going to take that region and rotate it around the full volume. So let's talk about theta. Over what range of theta values do we need to kind of encompass this entire volume? Theta needs to go all the way around, the full 360. So theta needs to go from 0 to 2 pi. And if we do that, you can imagine that these green traces in the phi direction are going to cover the whole volume. Okay, so what's left to do here? You're asked to calculate the volume, which means the integrand in this case is just 1. And now we're ready to integrate. Once again, because the limits are constant and the integrand is kind of separable into each of the different variables, we can separate this out into 3 different integrals. 0 to 2 pi d theta times 0 to pi over 4 sine of phi d phi. I need to erase that little speck there and there, d phi. And then finally 0 to 1 rho squared d rho. And you can do each of those single integrals individually and multiply the results. Here we get a 2 pi. Here we're going to get, we're going to integrate sine phi, get minus cosine phi. We'll plug in pi over 4 and 0. And what are we going to get? We're going to get 1 minus root 2 over 2. And then finally, integrating rho, we get rho cubed over 3, plugging in 1 and 0, we're going to get 1/3, and this will net out to 2/3 pi times the quantity 1 minus root 2 over 2, whatever that is. All right, I encourage you to break up these integrals like this whenever possible. It can really simplify the calculation and help you avoid errors. 266, we've got this bold-faced t in there, so that's a suggestion that we want to use a computer to graph the solid and to maybe do the integration. All right, so here what you're given is an integral that's clearly in cylindrical coordinates, and you've got these limits, and your goal is to kind of figure out what these bits are. Now, our usual tool for graphing stuff is GeoGebra, but GeoGebra is not very good. I mean, it can do cylindrical and spherical coordinates, but it's a little bit of a chore. And so we're going to jump over to Sage, and for maybe the first time this semester, look at some of the graphics capabilities of Sage. Sage can handle cylindrical coordinates pretty well, and it can do spherical coordinates as well. I'll show you that with this example. So we're interested in z going from the surface z equals r to the fourth up to z equals r, followed by r going from 0 to 1, and then followed by theta going from 0 to pi over 2. So I've put together a Sage worksheet that'll handle this for us. And I think I have it here. And just to make sure, yes, this is exercise 266. So I'll just walk you through this. I'm not going to type it out for you. So the first thing you need to do if you want to use a different coordinate system is tell Sage which coordinate system you're going to use. So the incantation for this is t equals cylindrical, and then this syntax here is telling me that in the future I'm going to be expressing the height in terms of the radius and the azimuth, I guess. Hold on for a second. Okay, so when you define a coordinate system, this is really low level, but remember, computers have to be told everything. You're telling it, one, that you're using the cylindrical coordinate system. Two, that if you encounter a function in plotting, that function is going to be the height z in terms of the radius r and the azimuth theta. Furthermore, if wherever order matters, it's going to be r and then theta, radius and azimuth. So that's what all of this sort of signifies. Next, we're going to declare the variables, r, theta, and z. And finally, you don't have to do this, but if you want to see that what you're doing is correct, you can ask Sage to show you what the transform t looks like. And here we give it, we say the radius is r, the azimuth is theta, and the height is z, and it comes back with this coordinate, and this is essentially x, y, and z. It tells me what it looks like in rectangular coordinates. All right, now in problem 266 here, we know that the lower limit, we're integrating with respect to z. So the lower limit is z in terms of r and theta, but there's no theta, so it's just z equals r to the fourth. And the upper limit, the bottom, is r to the fourth, the top is r. And we are also given the option of telling Sage what the range of the r variable is and what the range of the theta variable is. So the range of the r variable is 0 to 1, and the range of the theta variable is 0 to pi over 2. This is essentially equivalent to telling it, you know, what's the interval in the x direction, what's the interval in the y direction. So that's convenient for us. We set the r variable and the theta variable. Make sure we do it in this order, the r variable first and the theta variable second, because of this ordering up here. And then if we run this set of commands, we'll see the two surfaces, the upper and lower limits of integration, on the same set of axes. And what we see is the upper limit of integration, z equals r, is this cone, and it's a 45-degree cone. Right, the side forms a line that's 45 degree. And then the other one, z equals r to the fourth, is not one that we're super familiar with, but you can imagine, right? Z equals r squared would be sort of parabolic. Z equals r to the fourth is just more so, right? It's a parabolic kind of shape. And then we have, if you kind of look at this from a few different angles, we see that from the top, r is going from 0 out to 1, and then theta is going from theta equals 0 up to theta equals pi over 2, and that is it. So this is a visualization of the volume, and the volume that we're interested in is between these two surfaces. Z goes from the lower r to the fourth to the upper r. R goes from 0 to 1, and theta goes from 0 to pi over 2. That's it. So there's our visualization. Finally, we can do this integral, and let's use Sage to do the integral as well, just to remind ourselves how this works. Once you have an integral set up in Cartesian, cylindrical, spherical, what have you, that process is the same. It's just integrating with respect to each variable from the inside out. So I don't remember if I've actually done this. Yeah, calculate the integral. So here I just do the triple integral all at once. I integrate the integrand r, first with respect to z from r to the fourth to r, then with respect to r from 0 to 1, then with respect to theta from 0 to pi over 2. I execute that and I find that the volume is pi over 12, and as a number, as a floating point number, it's 0.26. So there's really not much to write here other than that the volume works out to be about pi over 12, which is approximately to 4 decimal places, 2618. All right. I'll post a link to this Sage worksheet in case you want to play around with it. It also has spherical plotting in it, which we'll do in a minute. All right, let's continue. Exercise 272. B is bounded above by the half sphere with z greater than or equal to 0, and below by the cone 2z squared equals x squared plus y squared. I'm going to do another side view first. Side view. And our side view again is going to be, this is the xy plane, and this is the z axis. All right, so if we were to look at this thing in the xy plane, this is a sphere of radius 4. 1, 2, 3, 4, 4, 4, 4, and we can sketch that in like that. That's what this sphere looks like from the side. And we've also got this cone, 2z squared equals x squared plus y squared. If we solve for z, we get z is equal to 1 over root 2 times the square root of x squared plus y squared. In cylindrical coordinates, that would be root 2 over 2 times r. And remember, when we look on this side view, we can consider this the r-axis if we want. So that is a line in the RZ plane with slope root 2 over 2. Root 2 over 2, if you may remember, is around 0.7. So we're going to get a cone whose edge kind of looks like that on both sides, and its cross-section is circular. Okay, so let's think about how we want to do this. This is similar to the earlier exercise with the cone and the sphere. It's just that the cone is a little bit wider than the cone in the previous example. So we probably want to do spherical coordinates here. And integrating in the rho direction, we're always starting at the origin and going out to the sphere. So we're going to go do d rho, d phi, d theta. In spherical, it's always r squared, rho squared sine phi. And the integrand is z here. So remember, what's z in spherical coordinates? It's rho cosine theta. So we get a rho cosine theta here, and I'll just remind everybody that that's z. And then we're going to integrate with rho integrate phi, integrate theta. We've got to figure out these limits of integration. If we're going to do rho, and rho always starts at 0 and goes out to the sphere, that's going to be 0 to 4. Now, if we're going to do phi, we're going to start at the North Pole and go out. So we're always going to start at phi equals 0. Here's the tricky bit now. How far out are we going to go? We need to figure out what this angle is. What is this angle in here? Well, how do we figure that out? That's going to be where this line intersects this sphere. So we need to figure out where's this intersect. All right, well, let's do that. It's going to intersect when let me just check my notes here. Hold on for a second. So to find that angle, we need to find that intersection. If we look closely at these two equations, we see that 2z squared is equal to r squared. And in the other equation, we see that r squared plus z squared equals 16. So in the second equation, we see r squared is equal to 2z squared. So let's replace that. 2z squared plus z squared equals 16. That means 3z squared equals 16. Z is equal to plus or minus 4 over root 3. And that tells me this height right here. The height of this intersection is actually 4 over root 3. I also know, because this is the radius of a sphere of radius of 4, that side is 4. So now I know that the cosine of the angle, the cosine of the question mark, is equal to the adjacent over the hypotenuse, 4 over root 3 divided by 4, or 1 over root 3. And the question mark is now the arc cosine of 1 over root 3. So that's the upper limit for the phi variable, arc cosine 1 over root 3. Definitely a bit of trig there to figure that out. So phi starts at the North Pole and goes out to this angle, which we've just determined is the angle that gets me to the surface of the cone. Finally, theta gets me all the way around the z-axis, so theta is going to go 0 to 2 pi. And I'm sorry, I made a mistake here. This z, the transformation for z in spherical coordinates is not rho cosine theta, it's rho cosine phi. Apologies for that. Let me fix that up here too. Rho cosine phi. Okay, we now have a complete integral, right? We've got all the pieces, we've got the integrand, we've got the limits of integration, and it's now up to us to actually calculate this integral. Let me make a little bit more space. I'll walk you through that. So, the volume here, not the volume, just the integral. If it were volume, this would be 1 here, but this is z. All right, so this integral, let's see, theta. There's no thetas anywhere, so we can do this theta integral right off the bat, 2 pi, right? Theta, everything else is constant, 0 to 2 pi, that's 2 pi. Let's see, can we do the, yeah, we can separate this out completely. So we get theta, we get 0 to arc cosine 1 over root 3. What's that going to be? Cosine phi, sine phi? Cosine phi, sine phi, d phi times 0 to 4 rho cubed d rho. And we can do all these integrals separately. 2 pi. This integral in the middle, let's integrate this guy so that we get minus cosine squared phi, right? We could have integrated it so that we got sine squared phi, but I'd like to keep that cosine and hope that it cancels with this arc cosine. So that looks good. It looks like I need an extra factor of 1/2 there to make that work out, but yeah, that looks good. And that's going to go from 0 to arc cosine 1/√3. And then this last guy, rho to the 4th over 4, plug in 4, plug in 0. That's 4 to the 4th over 4 minus 0. That's just 4 cubed. All right, let's keep going. 2 pi times 4 cubed from the rho integration. Let's plug in the arc cosine of 1/√3. Arc cosine goes in here, cancels with the cosine, turns into 1/√3. You square it, that's 1/3. With another factor of minus 1/2, that's minus 1/6. Plug in 0 here. Cosine squared of 0 is 1. Subtracting, that's going to be plus 1/2. Let's see, that's really 3/6 minus 1/6, 2/6, 1/3. 2 pi, 4 cubed times 1/3. Final answer. All right. Let's see, convert the integral given in Cartesian coordinates to an integral in spherical coordinates. So the goal here is to figure out what kind of shape is being described by these limits of integration. The integrand is not super important at this stage. This looks like we're doing dz dx dy, so this is z equals square root of 16 minus x squared minus y squared. And if you square both sides, you get z squared equals 16 minus x squared minus y squared, or x squared plus y squared plus z squared equals 16, and that's our friendly circle of radius, our friendly sphere, excuse me, of radius 4. All right, if you take that sphere and you squash it into the xy plane, you're going to get x going from here to here, and that's just a circle of radius 4. And then finally you take that and squash it down onto the last variable, y. It's going to go from the interval minus 4 to 4. So this is really just integrating the entire volume of a sphere of radius 4. So all of this together is a sphere of radius 4. And that's an integral that we can do in spherical coordinates. Rho goes from 0 to 4. Phi goes its full extent from 0 to pi, north pole to south pole. And theta goes all the way around 0 to 2 pi. The integrand is x squared plus y squared plus z squared. That's rho squared. And then we get another factor of rho sine phi from the spherical coordinate transformation, and then finally d rho d phi d theta, like that. This is an integral that we can separate into pieces, and in fact we can do the theta integral right off the bat, 2 pi, the integral from 0 to pi of sine of phi d phi times the integral from 0 to 4 of rho cubed d rho. This looks really familiar to the previous example. That's okay. 2 pi. The rho integral is rho to the 4th over 4 from 4 to 0. That works out to 4 cubed. This guy is going to go up to minus cosine phi, and we're going to evaluate that from 0 up to, excuse me, not 0 to 4, 0 to pi. Plugging in pi, plugging in 0, subtracting, we're going to get 2. So that's 2 pi times 4 cubed times 2. Final answer. You could clean that up a little bit more. In fact, 2 times 2 is 4, so we get another power of 4, so that could be 4 to the 4th times pi. That's a nice clean result. Okay, in 288, again, we're using a computer to look at the solid and then find uh, the volume. The difference here is we're doing this in spherical coordinates, so I'm going to jump over to that same Sage worksheet and show you how to set up spherical plotting. Um, this is rho squared sine phi, so it's just the usual factor that comes with spherical coordinates. Rho d phi d theta, rho goes from 0 to 1, phi goes from 3 pi to pi over 4. That's a typo. In fact, I've already informed the authors of this. That 3 should be up here and gone down there, because remember, we always want our limits of integration to be increasing. So phi starts at pi over 4 and ends at 3 pi over 4. That's increasing. And then finally theta goes from 0 to 2 pi. Let's see what that looks like in spherical coordinates. Alrighty. So now we're going to set up a spherical coordinate system. So we tell it, hey, we're going to use the spherical coordinate system. We want the radius as a function of azimuth, which is theta, and inclination, which is phi. So this determines the order of things. So we're going to specify functions theta first and then phi. We set up this transformation and we declare the variables rho, phi, and theta. And we actually can look at the transformation, and this is consistent with what we know of the spherical to Cartesian coordinate transformation. And then finally, we just want to plot. We want to plot the sphere radius rho equals 1. Rho equals 1. Right? That's what's going on right here. Rho goes from 0 to 1, so I want to see what that outer limit looks like. So it goes from 0 to 1, and theta is going to go all the way around, and phi is going to go from pi over 4 to 3 pi over 4, and we're going to plot it according to this transformation. And this is the shape that we get. Now this is just the outer shell for rho equals 1. It would actually be filled in. Boy, how can I sketch that? Let me go, I'm going to pause this and go figure it out. Okay, so apparently when I turned this back on, way back when I recorded this, I forgot to turn on the microphone. And what you're watching me do is try to fill in the rest of this figure. So I've got the outer part of this shell, but what's weird about this is there's sort of it's a solid, and I need to kind of figure out how to put the cone inside to kind of indicate the inner boundary of this figure. So that's what I'm doing now with my hands. I'm describing how I've got this cone that I need to embed inside this outer shell to get the full picture of the solid. Now, this is going to involve a little bit of Sage, and you'll see me kind of walk through it in a second. So I'm just going to pause here and just kind of narrate what's going on. So here I'm showing the outer shell, but it doesn't have its interior limits. So I had to actually go away and figure out how to do a new transformation. And here you're going to see me start to define a transformation where instead of having rho as a function of azimuth and inclination, I'm going to have inclination as a function of radius and azimuth. And I actually start to go through it here, and then you're going to see me jump to the bottom and build the cone separately, and then put it all together with this sphere. So there's me defining a different spherical transformation where I have inclination listed as a function of radius and azimuth, inclination being phi, radius being rho, azimuth being theta. So here's me giving up and deciding to go down below, but I'm also having trouble with basic copy and pasting. So now I'm going to go down to the bottom and just start again. So there's that spherical transformation. And now what I'm going to do is plot the equation phi equals pi over 4. That's going to give me the upper part of this conical shape that I'm trying to embed inside the spherical shell. Rho equals pi over 4, phi equals pi over 4, radius can be anything, azimuth can be anything. So I'm going to list radius rho going from 0 to 1, because that's the range that I'm interested in, and azimuth theta going from 0 to 2 pi. And when I execute this, you'll see a cone traced out. And that makes sense, right? Because that's the collection of points for which phi is equal to pi over 4. And there you have it. So that's a 45-degree cone, and it has a length of 1 along the side as rho goes from 0 to 1. And then I think what I do is plot 3 pi over 4, and you'll see that that's the bottom part of the cone. What I really want is both the top and the bottom, and then ultimately I want to embed them inside the spherical shell that I started out with. So this has turned out to be a far more complicated figure than I thought it would be. So here's me storing the bottom part of the cone in a variable called bot. And now I'm going to store the pi over 4 version in a variable called top. And then I'll show bottom plus top, which will plot both of them on the same coordinates. And then the last move is to just take those and stick them inside the spherical shell that I started out with. It looks like I'm going to change the color to red just to kind of emphasize which is the top and which is the bottom. Green for the bottom, red for the top. There you go. Not sure what I'm talking about here. Oh, I guess I decided to add a little bit of opacity here so that we can really see the structures so that they're not completely blocking each other visually. So opacity means that the figures are slightly transparent, so they don't block the view of the other thing when they get in the way. Okay, now maybe I'm ready to go stick this inside. Yeah. Okay, so now I'm going to store that thing in the sphere variable. And there's the sphere still there. And now I'm going to just go add sphere to top and bottom. And we get the cone neatly embedded inside the sphere. And you know, if I were really doing this right, I would make the sphere slightly transparent so that you could see through the blue side. Who knows, maybe I will. The suspense. Or maybe not. So anyway, I guess I went through plotting that. And now I'm just going to compute the volume. And that just is a matter of doing the integration, the triple integral. And I guess I'm going to do it from the inside out. So rho squared sine phi, and we'll do it from rho equals 0 to 1. probably, yeah, I'm going to store that. Oh, no, I'm not going to store it. I'm just going to add the next integral. Phi from pi over 4 to 3 pi over 4. And then finally theta from 0 to 2 pi. And let's see what that is. Okay, 2 root 2 over 3 times pi. So that's the volume. And I guess I'll go through and get a numerical approximation of that by using the n operator. About 2.96. That's it. So that was a relatively advanced exercise in visualization with SAGE. In 295, we have a charge cloud contained in a sphere B of radius r centimeters centered at the origin, and it has a charge density given by Q of x, y, and z. It's just proportional to the square root of x squared plus y squared plus z squared, which you should recognize immediately as rho. So it's proportional to the distance from the origin. K is some constant of proportionality, it's positive, and the total charge is essentially integrating Q over the volume. So let's make sure that we understand the limits of integration and convert this thing to spherical coordinates. It's spherical coordinates largely because the domain of integration is a sphere. It also happens that Q is going to express very nicely in spherical coordinates. So we have d rho d phi d theta, and then the Jacobian rho squared sine phi that comes with spherical coordinates. And then we have an additional factor of rho because the square root of x squared plus y squared plus z squared is rho. And then k rho is the function q expressed in spherical coordinates. Now we're going to integrate over the entire sphere. The sphere is of radius r, so we're going to go from 0 to r, 0 to pi, and then 0 to 2 pi. This is half the battle, setting it up. The rest of it is just stuff that you learned in Calc 2. So integrating with respect to rho and phi and theta. And you can do the theta integration right away. It's 2 pi. The constant k can come out, and that leaves behind an integral in phi and an integral in rho. You can do the phi integration. The phi integration is just, the antiderivative of sine phi is minus cosine phi. Plug in pi, plug in 0, and you're going to get 2. The rho integration, rho cubed over 3. Looks like I made a mistake there, maybe? Oh no, that is a rho cubed. I'm just not looking at it right. Yeah, so it's rho to the 4th over 4 plugging in 0, plugging in R, and we're all done. All the exercises are on the table here, and when you're finished, go ahead and hit C5S5 on WebWork.